Ford originally contacted me with a need for a leak-free fitting. It suddenly struck me that there really was no point in reinventing the wheel, and if something existed in the marketplace which would do the job, we would just incorporate it in our product line and sell it to Ford and advise them on its use, etc. So I did an analysis of the marketplace as it existed at the time. I'd been in America maybe 4 months at this time and wasn't familiar with everything that was available. This market analysis brought me to the understanding that there were basically 3 types of fitting in the marketplace. The first was the metal-to-metal, 37-degree or 45-degree flared fitting. These make use of the mechanical advantages associated with a taper. The problem with them is, first of all, they require very high torques in order to urge whatever defects exist in the metal-to-metal faces out of the interface, which would otherwise create leaks. So you need very high torques to bring those faces together and create a seal. And sometimes you have to do that 2 or 3 times because the first or second shot doesn't do it. In a metal-to-metal face, there's no secondary seal. You have a seal, metal to metal. And of course, if having first torqued it up, you don't get a seal, it's then necessary to go back and torque it again. And the result of that is that you would drive the male component deeper into the female component. If then you don't get a seal, you go back again and torque it yet further. And what's happening each time is that oil is getting out into the threads and creating a more lubricitous interface. And the more torque you apply, the further it drives down. And you get nose collapse, which, because once you've got a seal, you're never going to take that fitting apart again, is actually not recognized by many people in the industry. But the nose collapse does occur, and it can be quite significant. Vibration is a major feature of almost all hydraulic equipment. The pump creates vibration. Traveling across the ground, if it's a mobile equipment or a car, creates vibration. The engine driving the pump creates vibration, and all these vibrations, the sum of them, is very destructive to the metal-to-metal interface and will lead ultimately, in many, many cases, to failure. Expansion and contraction during temperature changes is a major problem. Hydraulic shock and pressure spikes in systems will give rise to a slight modification of the thread form and the association of the female threads with the male threads. There will be a movement, a settling in, which could give rise to a leak path, metal to metal, and there's nothing in there to counteract that leak path. And finally, if there's any defect from poor machining or bad handling subsequent to machining, which may not actually be visually obvious, but nevertheless functionally detrimental to the interface, then that defect is going to be hard to correct during the assembly process, and it may be that you can't completely correct it, and that fitting would have to be removed and replaced. So metal-to-metal fittings do have problems associated with them. They've been functionally really the best for 40 years, these tapered fittings. The second fitting of the 3 is the K-seal fitting, or KC fitting, which is used substantially in the aeronautics industry and has had a great deal of success, but which also has been proved to be prone to failure over time. This fitting is essentially a 37-degree fitting with an O-ring on the tapered interface, but the O-ring is larger in cross-sectional area than the groove that holds it. So when this is assembled, during assembly, the O-ring is crushed and then extrudes into the interface between the metal-to-metal faces, preventing metal-to-metal contact. And the O-ring is used as a gasket, as we're familiar with the word gasket. And the third fitting is the flat-faced O-ring seal fitting, the ORS, which is similar in design and principle to the CAT flange, the SAE flange fitting. where the O-ring sits in a groove which is larger in cross-sectional area than the O-ring. But the O-ring is, the groove is imposed on the flat face of the fitting, and the stock sizes have to be larger than the industry is used to with the 37-degree type fittings. And in order to get the torques up to sealing levels, they need a more exotic material than we're used to using in the hydraulics industry, which is more expensive to machine and more expensive to buy. In this system, the O-ring is the only seal. There is no backup seal to the O-ring. This can be easily demonstrated when you take the O-ring out and assemble the fitting. It doesn't matter how much torque you apply, you will not obtain a seal. It's subject to failure due to misplaced O-rings. During assembly, it is easy to misplace the O-ring in the interface, or even to completely eliminate it. The O-ring can drop out if you haven't got visual access to the point of assembly. The O-ring can actually become totally dislodged, and the fittings will be assembled without it being there, and nobody will know the difference until the system's pressurized and you get a big leak. During assembly, it is possible to misalign the O-ring and misalign the fitting, the result of which will be an O-ring which gets nibbled during assembly, and the result of that will be a less obvious leak, but nevertheless a leak which will worsen over time. Another major point is that the O-ring is always in contact with the pressurized medium and therefore subject to the same effects by the pressurized medium on the polymers of the O-ring as were described with the K-seal fitting. As I described, the torques required to assemble it are very high, and this can be a problem during assembly if the fitting is in an area where it's difficult to get at. You can't get the wrench into place to get the adequate assembly torques. And if those torques are not attained, you do not build into the assembly the required elastic memory invocation to keep it together. If you can't get the torques up to the level required to invoke the elasticity of the threads, then the interface is subject to vibration failure. The pressure in this system works entirely against the interface. There is no benefit to the interface incorporated in the pressurization of the system. The axial force of the pressure in the system is working to separate the components, working against that flat-faced interface, and there's nothing to counteract that to work for the assembly. So as you can see in the three systems described, there are no backups to the single seal that exists, either metal to metal or gasket elastomer or dynamic elastomer. In these three systems, there is only the one seal. This struck me at the time as fundamentally inadequate. An O-ring will work, but if it isn't protected from the medium, it'll deteriorate quickly. It'll only work in certain circumstances, and if those circumstances are not right, then it will be prone to failure. And metal to metal will work if the circumstances are perfect, but where those circumstances are less than perfect, failure will occur. If we could combine the two, however, we might have a much more acceptable situation. If, for instance, we can protect the O-ring from the pressurized medium to a large extent, if the O-ring were really only needed in the event of a failure of other seals, then we might have something which was significantly more reliable.